Okay, good afternoon, everyone. See, the last lecture we have started the unit number 6, that is design of beam, and we have started the design procedure of the beam. So, design procedure of the beam. I think 4 to 5 steps we have covered. Okay, so step 1 was the calculate factored load. Then maximum bending moment and shear force. That was the first step we have seen. Then step 2 we have seen, that is calculate plastic modulus. Then step 3 we have seen, classify the section. Then step 4 was design of shear strength. Design of shear strength for resistance. And step 5 we have started, that was design of bending moment. So in the design of bending moment we have calculated the bending moment for the unsupported supported beam. So we have calculated bending moment for supported beam. Laterally supported beam. Okay, so now up to this we have covered last time in the last lecture. So today we will see the bending moment for laterally unsupported beam. So bending moment BM for laterally unsupported beam. Okay, so for laterally unsupported beam, how to calculate bending moment? So the formula is MDR is equal to MDR is equal to beta B into ZP into FBD. And for laterally supported beam, instead of this FBD, FY was there. See, for laterally supported beam, the bending moment for laterally supported, design bending moment for laterally supported beam, in that here Fy was there, and in bending moment for laterally unsupported beam, here FBD is there. So this is the difference, FBD. So now, so what is FBD? So here, so where FBD is equal to, because beta B and ZP we know, beta B value of beta B is 1 and ZP value we have calculated in step number 2. But how to calculate FBD? That FBD is equal to design bending design bending compressive stress. Design bending compressive stress. So how to calculate this FBD? So FBD is equal to here zeta LT into Fy divided by gamma m naught. So FBD is nothing but here only zeta LT we have to add. So what is zeta LT and how to calculate zeta LT, that we have to see. So see here, so zeta LT is equal to now, zeta LT is equal to bending stress reduction factor. The zeta LT is the bending stress reduction factor reduction factor. Due to torsional effect, the bending stress will be reduced. So here, that is the zeta LT is the bending stress reduction factor. So how to calculate zeta LT? So zeta LT is the 1 divided by phi LT, 1 divided by phi LT plus in bracket phi LT square minus lambda square LT raised to 0.5, and it should be less than 1. It should be less than 1. So see, we have to calculate FBD. For FBD, formula is zeta LT Fy divided by gamma m naught. So here Fy and gamma m naught is known. So zeta LT is unknown. So zeta LT is equal to 1 divided by phi LT plus phi square LT minus lambda square LT. So now here we have to calculate this phi LT. So how to calculate phi LT? So phi LT is equal to, again formula is there, 0.5 1 plus alpha LT 1 plus alpha LT in bracket lambda LT minus 0.2 in bracket, sorry, bracket complete, plus lambda square LT. So in this way phi LT we have to calculate. But here, before calculation of phi LT, we have to calculate this lambda LT. So how to calculate lambda LT? So lambda LT, just minute. So here lambda LT we have to calculate by using the formula, that is lambda LT is nothing but here non-dimensional slenderness ratio. Slenderness ratio. See slide, this part is slight difficult and lengthy. हा जो अनसपोर्टेड लॅटरली अनसपोर्टेड बीम साठी जो काय हा पार्ट आहे बेंडिंग मोमेंटचा, हा थोडासा लेंदी आहे. जर एक्झाम मध्ये तुम्हाला अनसपोर्टेड बीम विचारलं तर बेंडिंग मोमेंट तुम्हाला या फॉर्म्युल्याने कॅल्क्युलेट करावी लागेल. सो लॅम्बडा LT इज दी नॉन डायमेन्शनल स्लेंडरनेस रेशो. Even though it is lengthy, we have to calculate because as per procedure we have to go. Okay, so how to calculate lambda LT? So lambda LT is again under root of beta B into ZP into Fy divided by MCR. MCR. Okay. Now here again MCR is the unknown. See, in each formula one unknown is there. So now here what is MCR? So MCR is the elastic critical moment. MCR is the elastic critical moment. Elastic critical moment. Elastic critical moment. Now how to calculate MCR? So MCR is equal to here now under root of MCR is the under root of pi square E Iy. Iy is the moment of inertia about y axis. Pi square Eiy hf divided by 2 LLT square. 2 LLT square in bracket 1 plus 1 by 20 again bracket LLT divided by RY divided by HF divided by TF bracket complete square. So this is the MCR, elastic critical moment, that we have to calculate. So by using this formula, and now here again unknowns are there. That unknowns are, so that unknowns are, write down again, where capital E, what is capital E? Modulus of elasticity. Capital E is the modulus of elasticity, and the value of modulus of elasticity for steel is 2 into 10 raised to 5 Newton per mm square. Then second unknown is the Iy. Pi is everybody knows. Pi value is everybody knows. Is Iy. Iy is the moment of inertia. Moment of inertia about y-axis. Then next unknown is here HF. HF. So HF is the center to center distance. Center to center distance between flange. So center to center distance between flange means these are the two flange. So center to center distance between these two flange. This is the HF. So how to calculate HF? HF is the H minus TF, because total this value is H. This is thickness of flange, again this is thickness of flange. If we minus one thickness of flange from this, so we got the center to center distance between these two flange. So HF calculated by H minus TF. Then what is TF? TF is the thickness of flange. TF is the thickness of flange. Now the remaining is the LLT. What is the LLT? So LLT is remaining. So LLT is effective length for effective length for effective length for lateral buckling. Effective length for lateral buckling, or we can say here torsion, lateral torsion. lateral, torsional. Okay, and what is remaining now? All the ry is remaining. ry is the radius of gyration. Radius of gyration about y-axis. And one more parameter is remaining, that is alpha lt is here remaining. So the value of alpha lt, so alpha lt is equal to actually this is the alpha lt is imperfection factor. Alpha lt is the imperfection factor, and that imperfection factor is 0.21 for rolled section and 0.49 for welded section. So rolled section means whatever section we have taken from steel table. The sections available are in the steel table. These all sections are the rolled section. And if the welded section, rolled section म्हणजे welded section सुद्धा steel table मध्ये available आहेत, but the standard size section जो आहे तो rolled section म्हणजे ISHB, suppose for example ISHB 350, ISMB 250, these are the rolled section. But if with addition of additional plate, आता इथं जर additional plate जर प्रोव्हाइड केल्या आपण आय सेक्शनला किंवा हे एकमेकाला वेल्डिंग करून जर आय सेक्शन तयार केला, सो दिस सेक्शन इज दी वेल्डेड. सो दॅट मेन्शन इन एक्झामिनेशन, सॉरी इन दी प्रॉब्लेम स्टेटमेंट, rolled section or welded section. The rolled section असेल तर alpha LT value we have to take 0.21, and if the welded section is there, that time we have to take alpha LT value is 0.49. That mentioned in problem statement. Even if not mentioned, then we have to assume and take rolled section or welded section, no problem. So this is the MDR. Okay, so for for here MDR for laterally unsupported beam, from here we have MDR is the beta B into ZP into FBD. So for FBD calculation we have seen so much formulas here, you can see here. So this so much formulas we have calculated for the calculation of FBD. So FBD is actually this is the torsional stress generating in the beam due to lateral forces. So again here check for bending moment is now check for again BM is the what? So MDR is greater than MD. So this is the step 5. So step 5 was over here. Now step 6. Step number 6. So step number 6 is check for design of beam. Check for design of beam. Now we have to take checks, 3 checks we have to take. check for wave crippling, check for wave buckling, and check for deflection. Okay, so now first check, so that is small a. So check for wave buckling first. Check for wave buckling. Now for check for wave buckling, that is, or we can say here buckling strength we can say. So yep, check for wave buckling is the FWB. See, so FWB is nothing but here F is the strength and WB is the wave buckling. So strength for wave buckling we have to calculate. We have to calculate here strength for wave buckling. So FWB is equal to, the formula is B1 plus 2N1 into TW into FCD. So this is the strength due to wave buckling. Wave buckling, strength of wave buckling. So here where N1 is equal to D by 2. So D by 2 is nothing but here depth of section by 2. Depth of section by 2. N1 how to calculate? Depth of section D by 2. Depth of section by 2. Now what is B1? So B1 is equal to here width of flange. Width of flange. See, whatever section we have selected, for that section this TW B1 are the dimensions are given in the your steel table. जो काही सेक्शन तुम्ही आय सेक्शन सिलेक्ट केला असेल त्याची डेप्थ, त्याचे B1 व्हॅल्यू हे तुम्हाला स्टील टेबल मध्ये अवेलेबल आहेत. ओके, देन व्हॉट इज TW? What is TW? TW is the thickness of wave. Thickness of wave. And then FCD is equal to compressive stress. FCD is equal to compressive stress. See, so how to calculate FCD, that everyone knows. So FCD value we have to calculate depends upon the buckling class. A, B, C, D, 4 buckling class are there. But so here for that purpose we have to calculate slenderness ratio first. So here to find FCD, calculate slenderness ratio. So how to calculate slenderness ratio? So slenderness ratio R is equal to here KL divided by RYY. So KL, or in one more formula here, KL, instead of KL here one more formula is for the beam is 2.425 into D divided by TW. This, by using this formula we can calculate the slenderness ratio. Okay, so again calculate slenderness ratio, and here buckling class is required again, and buckling class here write down FCD value. To find FCD we have to calculate plus slenderness ratio and buckling class. So FCD is here compressive stress, so slenderness ratio here we can calculate by using this formula. And now buckling class. So buckling class, is C. Buckling class we have to take C for beam I and channel section. C. Buckling class we have to take C when beam we are using I section or channel section. Always buckling class here we have to again select as a C buckling class. So now here by using, now we have solved so many examples. Slenderness ratio and buckling class is required for calculation of FCD. So we have to calculate, so we have to take buckling class C. Then on which page we have to go in IS 800 if the buckling class is C? So from table number 9C, table number 9C, page number 42, find FCD value. With the help of slenderness ratio and buckling class for Fy is equal to 250 MPa. For Fy is equal to 250 MPa, FCD we have to find. See, earlier this calculation we have did how to calculate FCD, how to go in on table number 9C, where is page number 42 for Fy 250. That calculations we have did, and we have to do here interpolation. FCD1 minus lambda 1 divided by lambda 1 minus lambda 2 into FCD1 minus FCD2. That formula for FCD calculation we have seen. Are you getting? Okay, so here in this way we can calculate this, sorry, so in this way we can calculate the buckling strength, FWB. Okay, so this is the buckling strength. The FWD is nothing but buckling strength we have calculated here. Then here small b, now we have to calculate here small b. Now small b is the check for wave crippling. So here wave crippling is nothing but FWC. FWB is the wave buckling strength due to wave buckling, here strength due to wave crippling. So here again P1 plus 2N1 into TW into Fy divided by gamma m naught. And where again how to calculate N1? So N1 is equal to here 2 into 2.5 into TF, thickness of flange. So this is the strength due to wave buckling. The wave crippling strength किती येईल, wave buckling strength किती येईल, that we have seen. And third is the check for deflection. check for deflection. Check for deflection. So now here one important point we have to write. That important point is write first note here. That note is for finding for finding for finding actual deflection, for finding actual deflection, for finding actual deflection, we have to take we have to take we have to take service load, or working load, service load or working load. We have to take service load or working load. So now we have to calculate the deflection. So here number one, for central point load, how to calculate deflection for central point load. For central point load, how to calculate deflection. So for central point load, delta actual is equal to, for central point load, delta actual is equal to anyone can tell me what is the deflection for central point load? Anyone can tell me?
WL square by 40.
Okay, WL cube, not L square. WL cube by 48 EI is the actual deflection for central point load. Correct? Only the here change is L cube, not L square. Good. Similarly, for UDL, what is delta actual? For UDL, what is delta actual? So delta actual for UDL is 5 WL raised to 4, 5 WL raised to 4 upon 384 EI. So here, what is EI? Where E is the modulus of elasticity, modulus of elasticity, and I is the moment of inertia. Okay, so that is the delta actual. So now we have to calculate here delta allowable. So delta allowable is L divided by 300. So delta allowable is L divided by 300 for point load or UDL, for both. And the check is, we have to take check. That check is delta actual is less than delta allowable. We have to check. If we calculate this delta actual and delta allowable, L is the length of beam is here. L is the length of beam. So delta actual should be hence hence okay.